All right, let's continue with mass spectrometer. Okay, this is section 7. It's the mass spectrometer. I mathed it out. If every student in my physics C class, all what, like 50 something kids, 50, I think 60 something kids, brings $1,545, then we can all collectively purchase one. Then every student can maybe get like 2 minutes of mass spectrometer time each class period. Okay, how does a mass spectrometer work? What it does is it measures the mass. Okay, of individual atoms. Okay, and molecules. Okay, and it counts how many molecules have the same mass. Basically, what it does is it counts the number of atoms and molecules that a substance has in it. Okay, so what you would do is you'd have a mass spectrometer. You can put a substance into it, and then what it will do is it will actually count those atoms. So let me walk you through step by step how the mass spectrometer works and how it works as magic. Right. The first step is that you put a sample of material, okay, into compartment S, okay, and evacuate the air, okay. When you put it into S, right, when you put the sample of material into the mass spectrometer, okay, and then it evacuates the air, what it then does is it vaporizes sample, okay. Now the individual, okay, atoms. So now individual atoms, I should say now. Okay, I don't have my whiteout with me. This is now. Individual atoms give each particle charge, okay, through ionization, okay. Then it accelerates the particles through potential difference. Okay, so you have the two plates, right? It shoots the particles through. Okay. The next step is that it sends the particles through what's called a velocity selector. Okay, it sends the particles through what's called a velocity selector. So then what happens is that there's this thing right here. Where is it? It should be, the velocity selector should be right here. Okay, it should be right about between the plates. And what happens, the way that the velocity selector works, and I'll talk about this a little bit more here in a second, is that if they're going a certain speed, then they will actually have a B field and an E field that cancel each other out, and then the particle will go straight. Okay, so that's how the velocity selector works, is that they want it to travel where it's undeflected through the crossed B and E fields. Okay, the particles then enter a B field, okay, region. That's this big half circle right here. They enter the B field region. They circle around, okay, and then collide with the detector. Okay. Then what happens is the radius of circle is used to get mass. Okay. The radius of the circle is used to get the mass. Okay. So um, um, they will, so then they can figure out, okay, well, what's the radius of the circle? They can work backwards from that equation that we derived in the previous part, which is QV, I have it right here, written here. MV over QB, right? And they can then use the data there. They know the velocity, they know the charge, and then they know the B field. They just need to, and the radius, so then they can get M by itself and figure out what it should be, okay? The velocity selector, how this works, right, is that if you send charged particle through, okay, the crossed E and B fields, okay, if the velocity is just right, okay, the charge moves in a straight line through E and B. Okay, and the reason that is because the E field force will cancel with, or sorry, will be equivalent and cancel with the B field force. Okay, it should be equals. I'm totally messing up right now. I don't have my white out. Okay, so it should be, they should equal each other. Okay, so they cancel out. Okay. Okay, let's go on to the next page here. Okay. Okay, so in each case, determine the direction of the electric field that could balance out the magnetic field's force. Okay, so there's a couple of steps that you have to follow here. First, okay, you need to first off figure out we need to figure out the direction of the B force. Okay, so find the B force. Okay, that's the first step. The second step is to is to know that the direction of the electric force would have to be opposite, and then for E field, it would depend on if it's positive or negative. So let's go through that really quickly. Okay, first off, we use our right hand rule because it's a positive charge. Velocity there, B field into the page. Okay, so we'll notice that the force is going down. Okay. So that means that our electric force, our E force, needs to go up. Okay? That means that our E force would need to go up. And for a positive charge, to get an upwards E force, then the E field would just also have to go up. Okay? Okay, for this one right here, positive charge, velocity going up, B field going out of the page. So then our thumb would give us a force, a B force to the right. Okay, so we need an E force to the left, and therefore we would then need a electric field pointing to the left because it's a positive charge. We would need an electric field going to the left. Okay. Okay. This one right here, negative charge moving out of the page, so we would have to use the left-hand rule, okay? Out of the page, B field going down, so we would feel the force, we should see the force going to the left here, okay? So we would need an E force going to the right to cancel that out. Now here's the thing, it's a negative charge, so it goes opposite, so the force on it would be opposite the direction of the magnetic field. So instead of it going to the left like you would expect, it's actually also going to go to the right. Okay. Here, right, the velocity is going into the page. This is right hand again, into the page, B field to the right, force is going to go up. Okay. Okay, that's going to be the B force right there. Okay. And then the E force is going to go down. Okay, because it's got to oppose it. And then what's going to happen is this is a positive charge, so the field would have to go down, right? Okay. And then right here, the negative charge, so use your left hand, okay? I can't twist my hand that way, right? B field going up. You should see that what's happening is the E field will, or sorry, what's happening here, okay, velocity goes that way. So the B field force, okay, is coming out of the page, okay? So that means that the E field force needs to go into the page, or sorry, yeah, into the page, okay? And then that would mean that the electric field would need to come, since it's a negative charge, it would need to go out of the page, okay? Okay, so that's what all the little dots are for, right? Okay. 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 Particle of mass m and a positive charge q is released from rest inside of a mass spectrometer as shown in region one. So this is the plates, right, where it's being accelerated. Then it's going to go into here. This right here, region two, should be the velocity selector, and then three is where it's going to make the radius to give us that. We're answering everything in terms of m, q, v, and b. Okay. So in order to figure out the velocity of the particle when it leaves region one, all you got to do is conservation of energy. Okay. Okay, conservation of energy. We have QV equals 1/2 mv squared. Okay, and then you'd have 2 QV. If you're multiplying 2 on both sides, you'd have 2 QV over m. That gives you v squared, right? So you multiply 2 on both sides, divide m on both sides. Now you got to do one last thing, and you just got to square root, which will give you root 2 QV over m. Now it's important to note, okay, this is lowercase v. I'm sorry I haven't made it very clear, okay? Um, this is lowercase v right here, okay? And then this is uppercase v. I'm going to kind of give it little lines so that you know it's uppercase v, okay? Because it's kind of hard to tell, especially with my handwriting, okay? Okay. To indicate how the electric field must be directed in order for the positively charged particle to pass through the region without being deflected. So it's a positive charge. It's going to be moving to the right. So right hand rule, B field out of the page. So we're going to know that the B force is going down. So the electric field should be going up. Okay. And you would determine that with your right hand rule. Okay. And then because of the direction of the because the direction of that is as we've just found, right, going from that, right, potential starts at positive plates, okay, and then ends at the negative, okay. And I don't have my red pen. I feel very lost without it. This is more, it looks like it's red, but it's actually like a brown, okay. Okay. To figure out the electric field, okay, in region two, the best thing to start with is Newton's second law, right? By first off stating that the electric field, okay, force must be equal to the B field force, okay? So then you would get QE is equal to Q lowercase VB, okay? Then what you recognize is you have a Q on both sides, so we can knock those out and make our life easier, okay? But you don't know what V is, okay? You don't quite know what V is yet. So what we need to do is we need to take this V, the velocity V, and replace it with this expression that we just wrote up here, okay? So when we do that, okay, you're going to end up seeing that this gives us E equals root 2QV over m times b. Okay? Pretty straightforward. That's all you got to do for that. Okay? Okay. An expression for the radius of the circular path in region 3. Okay? If we start out, so in the key, right, I started out with QVB equals mv squared over r, but if you remember that we did already write an expression for the radius, right, and it was just r equals mv over qb, we can actually just shortcut right to this. And the only thing that we need to do now is take our expression for velocity, okay, and plug it in for that, okay? So then you end up getting r equals m over qb, and then the v is just root 2qv, okay, over m. Okay, and that's the expression for the radius. It's really not that bad at all. Okay, And then to figure out the time that elapses from the time the charge enters region 3 to when it strikes the wall at the end of the path, this is also not that bad. Okay, this is also not too bad. All you got to do here is just take. I'm trying to find a color I haven't really used yet. I guess I'll use the regular blue. Okay. All you got to do is take your velocity equals distance. You know that velocity is distance over time, right? And we already have an expression for velocity. Okay. So what we're going to do is we're going to take the velocity equals distance over time. How much distance does it traverse? Well, it's going a half circle. So instead of normally it would go 2 pi r, right? But it's actually going to go half of 2 pi r, which would just be pi r, right? Okay, so that would be pi r, and the time it takes is just t. We don't know that yet, okay? Now, here's the thing, okay? What we want to do is we can actually replace our expression for r with the expression up here. Now, you can replace r with this whole mess right here, but this is actually going to cause you more work. If you actually take this part r right here and you just replace it with this, then you will actually you will actually save yourself a huge headache, because watch this, right? The velocity is equal to pi over t, okay, times mv over qb. And guess what? Now you should notice that there's a v on both sides. Oh, so let's knock those out, okay? And you notice that that actually saves you the trouble of having to plug in this whole root expression right here. This makes your rearranging way easier, okay? So you get 1 equals pi over t, or sorry, pi times m over t qb, okay? Multiply t on both sides, and that's all you got to do. This saves you a huge headache, okay? This saves you a massive headache having to do all of that that extra work, right? Now you don't have a root in the equation. All you have to do is just cancel out your v's, and then you just got to multiply t. If you actually replace the expressions, I think you could still, if you actually substitute the expressions, you'd have to substitute this v on the left-hand side for the root expression. You would see that they're the same. You can cancel them out. You're just writing more to get to the same result, okay? That's all it would be, okay? Let's see. Is that the last one? Yeah, that is the end of mass spectrometers. Okay, so I guess I'll see you on the next one.